exercise solution for chemical kinetics, and today we'll be doing question number 4.26 to 4.30. In 4.26 they have given decomposition of hydrocarbon, and for this decomposition they have given equation for rate constant, and we have to calculate energy of activation. So we'll write down this equation, that is equation given to us. So what is given to us is rate constant is equal to 4.5 into 10 raised to the power 11 per second. This is the value of pre-exponential factor for the Arrhenius equation, and then we have minus 28,000 K, that is Kelvin, divided by T, that is temperature. Okay, this is the equation given to us. And now we will write down the Arrhenius equation. According to Arrhenius equation, rate constant is equal to pre-exponential factor, then we have EA upon RT. Okay, so what we will do, we will compare these two equations, the equation given to us, that is first one and the second one. So when we compare first and second equation, so have a look here. This part, that is your minus EA by RT, is having the value this one. Okay, so we will write it down, and from this we will calculate the energy of activation, because we have to calculate EA. So it is minus EA over RT from our Arrhenius equation is equal to minus 28000 Kelvin divided by T. It is from the given equation. Okay, so from here this equation we can rearrange. It will be minus will cancel out. So we have energy of activation is equal to 28,000 Kelvin into R, that is gas constant. T and T will cancel out. This is equal to 28,000 Kelvin into value of R, that is 8.314 joules per Kelvin per mole. This Kelvin and per Kelvin will cancel out. So the value that we are getting here is 232.79 into 10 raised to the power 3 joules per mole. So energy of activation we can write as 232.79 kilojoules per mole. This is our answer, energy of activation. Okay, come to next question, 4.27. In 4.27, rate constant for the first order decomposition of hydrogen peroxide is given by the following equation. They have given equation for decomposition of hydrogen peroxide, and this is the given equation. Okay, calculate EA, energy of activation for this reaction, and at what temperature will its half-life be? 256 minutes. Okay, so what is given to us in this equation is log K is equal to 14.34 minus 1.25 into 10 raised to the power 4 Kelvin divided by temperature. Okay, this is given to us. What else they have given? That they are asking at what temperature. So we have to find out your temperature when T half is equal to 256 minutes. Okay. Now, from Arrhenius equation, as we have written before, in the log form, it can be written as log K is equal to log A minus EA by 2.303. We are writing 2.303 because we are not writing Arrhenius equation in the form of natural log. We are writing in terms of log to the base 10. Okay. So now we are getting two equation, one Arrhenius equation in the log form and one is given to us. So from both these equation, what we are getting in the same way as we did before, we can find out the energy of activation. That is this part and this part when we compare. So we have EA divided by 2.303 RT is equal to 1.25 into 10 raised to the power 4 Kelvin divided by T. T will cancel out both the side. So therefore, we can write as energy of activation is equal to 1.25 into 10 raised to the power 4 Kelvin into 2.303 into value of your gas constant, that is R. It is 8.314 joules per Kelvin per mole. So from here we are getting value as 239.34 kilojoules per mole. We have calculated this value in the same manner as we calculated in the previous question. Okay, so this is your energy of activation. That is our first answer. Next we have to find out temperature, where half-life is 256 minutes. Okay, so for calculating the second part, we will be writing your rate constant. Okay, so rate constant for first order reaction is K is equal to 0.693 divided by T half. This is equal to 0.693 and T half is given as 256 minutes. So we will be multiplying this with 60 to convert it in seconds. Okay, so we will be getting answer as 4. This value is in seconds now, okay, because we have multiplied with 60. So 4.5 into 10 raised to the power minus 5 per second. This is the value of rate constant. Now we will be putting value of K in equation number 1, that is given equation. So we will be putting the value. So first equation is log K value. We will be putting, so log of 4.5 into 10 raised to the power minus 5 per second is equal to 14.34 minus 1.25 into 10 raised to the power 4 divided by T. T we have to calculate in this case. Okay, so log 4.5 into 10 raised to the power minus 5, we can break it as log of 4.5 plus log of your 10 raised to the power minus 5. Okay, this is equal to 14.34 minus 1.25 into 10 raised to the power 4 divided by T. Now we will find out the value. Log of 10 raised to the power minus 5 will be minus 5 because log to the base 10 is 1. So we will be getting value as 0.654 minus 5 is equal to minus 5 from the second term, and we are getting this as the same value, that is your 14.34 minus 1.25 into 10 raised to the power 4 divided by t. Now we will simplify this. So 1.25 into 10 raised to the power 4 divided by t. We will bring this on left hand side. This is equal to 14.34 plus 5 minus 0.6542. So we are getting this value as 18.6858. So t can be calculated as 1.25 into 10 raised to the power 4 divided by the value we calculated, 18.6858. You will be getting value as 669 Kelvin. So temperature is 669 Kelvin. This is second answer. Temperature at which half-life will be what value? 256 per minute. That is this one. The temperature at which half-life will be 256 minutes will be 669 Kelvin. Okay, we are getting answer in Kelvin because all values are in Kelvin. Now next 4.28. In 4.28, decomposition of A into product has a value of K as 4.5 into 10 raised to the power 3 per second. Rate constant value is given at 10 degrees Celsius and energy of activation is 60 kilojoules per mole. At what temperature would K be 1.5 into 10 raised to the power 4 per second? In this question, they have given two rate constant values. First in the beginning, for which they have given temperature also, and the second one here we want to calculate the temperature. Okay, they ask you to calculate the temperature. For both the reaction, we will take the idea that energy of activation will not change. It will remain same for this given reaction. Okay, so the given information is A is given some reactant and it is decomposing into some product. For this, K initial value of rate constant is given, that which is 4.5 into 10 raised to the power 3 per second at temperature given as 10 degrees Celsius, which is equal to 283 Kelvin. Okay, and for this energy of activation is also given. Okay, this is the value of energy of activation. Suppose we take this initial K as K1. Okay, and your initial temperature for this case as T1. Now second K value which is given to you is 1.5 into 10 raised to the power 4 per second at a temperature which we will suppose as T2, and this value we have to find out. Okay, so we will be writing your Arrhenius equation. We will be writing the Arrhenius equation in the log form or in the form of log to the base 10. So first we will write down for the second constant. So log K2 is equal to log A. A will be same for both the cases because A is constant for a specific reaction, and the same idea we apply for energy of activation. That is, energy of activation is not changing. So 2.303 R T2. This is for the second rate constant. Similarly, suppose this is equation number 1. Okay, now similarly we will write down one equation for the first rate constant also, which is log K1 is equal to log A minus EA divided by 2.303 RT1. This is equation number 2. So from equation number 1 and 2, we can calculate this value, log K2 minus log K1 will be equal to log A minus EA by 2.303 R T2 minus log A minus EA divided by 2.303 R T1. Now here when we will open the brackets, log A and log A will cancel out because second log A will be negative value, and after simplification we can write the same equation as log K2 by K1, okay, is equal to EA divided by 2.303 R. This part, that is this part, is common in both the leftover terms, okay. So we will take it as a constant. Now the first term is having 1 by T2 here, and the second term is having your T1 here. So what we will be writing the value here as, the equation can be written as EA, then we have T2 minus T1 divided by T1 T2. Okay, we are getting, how we are getting, because the term, have a look here, this term 1 by T2 is of negative sign, and here 1 by T1 will be of plus sign, because here minus sign will change. Okay, so it will be 1 by T1 minus T2, or if you are not able to understand this, let us write in a simpler way first. That is the first term which is left here. Have a look here, what is left with minus sign, we are left with 1 by T2. So we will write it here, your minus 1 by T2, and the second one minus will become plus, and it is 1 by T1. So we can write it as 1 by T1. Okay, now we will be simplifying it as EA by 2.303 R, and we will be having values here T1 T2 T2 minus T1. Okay, we will put down now values. Log K2 and K1 values are already given to us, so we will write it as log 1.5 into 10 raised to the power 4 divided by 4.5 into 10 raised to the power 3. This is equal to, energy of activation is given to you. It is 60 kilojoules per mole. So 4 zeros we have to put joule for writing in joules per mole, divided by 2.303. R value is 8.314 joules per Kelvin per mole. Okay, in such type of numerical, always remember, if energy of activation is in kilojoule, unit of the gas constant should be in kilojoules, or both of them should be in joules, same unit should be there, otherwise we'll get wrong value. And here we have T2, we do not know what is the value of T2, so we will write T2 minus 283 divided by 283 T2. Okay, we can write it as log of, after multiplying the value, log of 3.33 is equal to 3133.63 after simplifying these values, and the same T2 minus 283 divided by 283 T2. You can simplify this equation and we will be getting value of T2 as 297 Kelvin. Okay, and if we want to write in degrees Celsius, so it will be, T2 will be 24 degrees Celsius, and you should report your answer in degrees Celsius, because in your question they have given the initial value of temperature have a look here in degrees Celsius. So your answer should also be in degrees Celsius. So convert Kelvin temperature into the Celsius temperature, scale. Come to next question, 4.29. In 4.29, they have given time required for 10% completion of a first order reaction is 298 Kelvin. Okay. And it is equal to that required for its 25% completion at 308 Kelvin. A value of A is given and we have to calculate rate constant at 318 and energy of activation. Okay. So two values are to be, we have to find out value of K and value of energy of activation. K at 318. So in this question, what we have in the very first line, 10% completion. What is the meaning of 10% completion? What is the meaning of 10% completion? So what we have, it is first order reaction. So initially, suppose if initial concentration or the amount is A, okay, and amount reacted is suppose X. So therefore this X is equal to 10 by 100, that is 10% of initial amount, which is A. So therefore this is equal to 0.A. So amount reacted is 0.1 times of the initial amount. This is the meaning of 10% completion. In the same way, we can write down for 25% completion also. Okay. So we'll start with the very first part, that is we will write down the rate constant value at 298 Kelvin, that is first temperature given to us. We will write down the equation for rate constant 2.303 for first order kinetics, and for this we will be writing T1, that is in the first case, that is first temperature value. This is equal to, first time taken divided by A minus X. We write it this way. So we will put down the values here. This is equal to 2.303 divided by time taken in the first case, and log of 100, initial value is what, A, divided by A minus 0.1A. This is equal to 2.303 divided by T1 log of, we have here after simplification 100 by 90, because 0.1 is there in the denominator. So we will be getting value as this is equal to the value is 0.1055 divided by T1. Okay. Or we can say T1 is equal to 0.1055 divided by K at 298 Kelvin. This is the value of T1. Okay. Similarly, we will write the other equation, that is K at 308 Kelvin. That is why we are writing, because second, for 25% completion they have given value. This is written as 2.303 divided by T2 in this case, log of A divided by A minus 0.25A. What is 0.25A? It is for amount value of X for 25% completion. That is the second condition given to us. And from after simplification here, we will be getting the value as K 308 is equal to 0.2879 divided by T2. Okay. Or T2 is equal to 0.2879 divided by K K308. This is second value of time taken. Now in your question, what is the condition given to us? Given is that time taken for 10% completion is equal to for 25% completion. Therefore, 0.1055 divided by K298 is equal to 0.2879 divided by K308. We will equate the equation, that is your these two equations, this equation number 1 and equation number 2. So we can equate and we are getting this equation, the third one. Therefore, we can write it as your K308 divided by K298 is equal to 0.2879 divided by 0.1055. This is equal to 2.7289. This value we have to remember because we will be using this value later on. Fine. Now what we have to calculate? We have to calculate K at 318 Kelvin. Okay, so we can write down Arrhenius equation at two different temperature. So Arrhenius from Arrhenius equation, okay, what we can write down, log of K2 divided by K1 is equal to energy of activation divided by 2.303 R, and then we have T2 minus T1 divided by T2 into T1. This equation we have already derived in the previous question. Okay, so now we will compare this equation with the equation number 3 and have a look here. K308 over K298 is nothing but K2 by K1. Okay, and for this value is 2.7089. So we will put down this value and other values and we'll try to find out the value of energy of activation. So here we will write the same equation as log K2 over K1 is 2.7289. Okay, this is equal to energy of activation divided by 2.303 into R is gas constant, which is 8.314. T2 is the final temperature is here. What is the final temperature? 308. Initial is 298. So 308 minus 298 divided by 308 into 298. Okay, so log of this value we will find out from the log table and value will be 0.4360 equal to EA divided by 2.303 into 8.314. And here we are getting difference as 10 and divided by 308 into 298. Now here we will be simplifying the right hand side, and after rearranging we will be getting value of energy of activation as this is equal to your 76.623 kilojoules per mole. Okay, now one more thing is left, which is K at 318 Kelvin temperature. This also we have to calculate. This is the value of energy of activation. So this is our first answer. Now we have to calculate one more value, that is value of K at 318 Kelvin. For this we will write Arrhenius equation in log form, which is log K is equal to log A minus EA divided by 2.303 RT, and the value we will put down log A value is 4 into 10 raised to the power 10, it is given to us, minus EA we have calculated 76.623 into 10 raised to the power 3 joules per mole divided by 2.303 into R value is 8.314 joules per Kelvin per mole into 318 Kelvin temperature. So we are getting value here for the first term as 10.6021 minus 12.5843 and log K is having value minus 1.9822. Now this value is negative, so and we have to take anti-log, so K is equal to anti-log of minus 1.9822. Now we have to change this value because we cannot take anti-log this way, so we can write it as anti-log of this value, that is fine, and this value will find out from the log table, anti-log table, and value of K will be 1.042 into 10 raised to the power minus 2 per second. This is the value of K. This is our answer for the second part, that is value of K at 318 Kelvin. Okay, so this is all for this question. Now come to 4.30. In 4.30, they have given rate of a reaction quadruples when the temperature changes from 298 Kelvin to 313 Kelvin. Okay, calculate energy of activation assuming that it does not change with temperature. Okay, so the information which is given to us is what we have at T1, that is the first temperature, which is equal to 293 Kelvin. Rate constant we can take as K1, and at T2, that is 313 Kelvin, rate constant we can take as K2. Now it is given to us, what is given, that is rate constant at 313 Kelvin will be 4 times of the one in the at 293 Kelvin. Okay, so K2 is equal to 4 times of K1. This is already given to you. They have used this term, a reaction become 4 times, okay, when there is a change in temperature from T1 to T2. So from here we can write as K2 over K1 will be equal to 4. Now we will write down Arrhenius equation in terms of 2 temperature. We have written it before. Log K2 over K1 is equal to EA divided by 2.303 R and T2 minus T1 divided by T2 into T1. We have derived this relationship. So we will put down the value of K2 over K1 from here, that is 4. So log 4 is equal to the EA divided by 2.303 into 8.314, and the values are 313 minus 293 divided by 313 into 293. Okay, log 4 value will be 0.6020. This is equal to EA divided by 2.303 into 8.314, and we have here value 20 divided by 91709. Okay, so EA will simplify as we have done in the previous case. It will be equal to 2.303 into 8.314 into 91709 into 0.6020 divided by 20. So this value is coming as 52.85 kilojoules per mole. This is the value of energy of activation. So this is our answer. This finishes our